Hello class, welcome to chapter 14. In this chapter we're going to discuss foam. And while water has been the main means of suppressing fires for many years and is certainly effective, foams have added a new dimension in fighting fires. With improvements in application techniques and versatility of foam concentrates, the use of foam for all types of fires is becoming more common. Among the many hazards that firefighters must contend with today are a wide variety of incidents involving combustible liquids and flammable liquids. Successful control and extinguishment of these incidents requires not only the proper application of foam on the fuel surface, but also an understanding of the physical characteristics of foam. A full understanding of foam and its application is imperative to a safe and successful suppression operation. In this chapter, the objectives we're going to cover are how foam works. We're going to describe the foam tetrahedron, describe foam characteristics, the different types of foam concentrates, and we're going to describe foam expansion rates. We're also going to describe foam percentages and their importance, foam guidelines and limitations, and the different types of foam application systems. Water has been the main means of suppressing fires for many years, and water is effective, bountiful, and relatively inexpensive to use. And while water is certainly effective, foams have added new dimension to fighting fires, as I mentioned in the introduction. Among the many hazards that firefighters must contend with today are a wide variety of incidents involving combustible liquids and flammable liquids, and successful control and extinguishment of these incidents requires not only proper application of foam on the fuel surface, but also an understanding of the physical characteristics of the foam itself. A full understanding of foam and its application is imperative to a safe and successful suppression operation. Lack of familiarity with the chemical characteristics of foam and its application can cause severe problems for both you and your crew. Know your equipment and always operate safely. Improvements in and greater simplicity of application techniques and the versatility of foam concentrates makes the use of foam for all types of fires more common. The National Institute and Standards of Technology, or NIST, has determined that foam is 3 to 5 times more effective than plain water in extinguishing fires, and this can justify its use and its added expense at an incident site. While foam has been available for firefighting for many years and was first used in the 1800s and was introduced as an extinguishing agent for flammable liquid fires, and this original foam was produced by mixing two powders, aluminum sulfate and sodium bicarbonate, with water in a foam generator. This method was used for chemical foam extinguishers as well. Inside the fire extinguisher, the two chemicals were stored separately. And then to operate the fire extinguisher, a seal was broken and the extinguisher was inverted, allowing the aluminum sulfate and sodium bicarbonate to mix and create the foam. In the 1940s, a foam concentrate based on liquid protein was introduced. This foam was made from natural animal byproducts. It was produced mechanically by mixing the protein foam concentrate with water in a foam proportioner. A foam proportioner is a device that mixes the foam concentrate into the fire stream in the proper percentage. And protein-based foam was primarily used to fight flammable liquid fires aboard Navy ships. In the 1960s, fluoroprotein foam, or FP, and aqueous film forming foam, or AFFF, were introduced. These foams were more versatile and performed better than protein foam. In particular, they were able to knock down fires faster than protein foam and had a longer blanket life. In the 1970s, alcohol-resistant foams became available. These foams could be used for fires involving hydrocarbon or polar solvent fuels. The introduction of alcohol-resistant foams allowed flexibility in dealing with the many types of fuels that firefighters encounter on a daily basis. While the use of foam has been limited in the past for many reasons, the technological improvements made to foams and the equipment associated with their application have made these agents' use more common and acceptable in today's fire service. As more fire apparatus have been equipped with foam systems, operation and maintenance of these systems has emerged as an important skill for the driver-operator. The knowledge necessary to properly operate and maintain these systems can only come from learning about and training with all the systems. Now, with the introduction of the automobile and the use of industry of petroleum products, firefighters soon realized that water was not effective for extinguishing fires involving these types of products. Water is heavier than petroleum, therefore its application to petroleum-fueled fires caused more problems than it solved. In fact, water would actually spread the fire and make the situation worse. A method was needed to deal with the growing use of petroleum products and the resulting incidents that occurred when these products ignited. Firefighting foam was one of the methods available to deal with these issues. So what is foam? The foam used for firefighting purposes is a stable mass of small air-filled bubbles. It has a lower density than oil, gasoline, or water, meaning that it will float on top of the fuel. The way that foam works to help extinguish a fire is very simple, and it's illustrated in figure 14-2. Once it's applied to the burning fuel, the foam will float and form a blanket on the surface. This blanket, if applied correctly, will stop or prevent the burning process by separating the fuel from the air, lowering the temperature of the fuel, and or suppressing the release of flammable vapors. Foam is created through the application of four components: water, foam concentrate, mechanical agitation, and air. First, water is mixed with a foam concentrate in various ratios to produce a foam solution. This solution must then be mixed with air by some form of mechanical agitation. In firefighting, this mechanical agitation usually takes the form of a nozzle that mixes the air and foam solution to form the final product. The final product is referred to as finished foam. The ratio of water to foam concentrate is critical. Too little foam concentrate in the water will produce a foam solution that is too thin or lean to be effective and may quickly dissipate into the fuel itself. Too much concentrate will produce a foam that may be too thick or rich to be properly expanded or aspirated when mixed with air. The expansion of foam solution depends on good mechanical agitation and effective aeration, which is the process of introducing air into the foam solution. When an insufficient amount of air is introduced into the solution stream, the solution is poorly aerated, and this results in foam with too few bubbles. Fewer bubbles causes the foam to break down so quickly that it does not suppress vapors effectively, and poorly aerated foam will also break down quickly when exposed to heat and flame. So let's discuss the foam tetrahedron. A foam tetrahedron depicts the elements needed to produce finished foam, and that's shown here in this slide, which is also in your book and is figure 14-3. If any of the elements of the tetrahedron is missing or not present at the proper concentration, foam production will be affected. This results in poor quality, ineffective foam, or no foam being produced at all. The foam tetrahedron requires four components: water, foam concentrate, air, and mechanical agitation. And foams come in two basic types: chemical foams and mechanical foams. Chemical foams are produced through a reaction between two chemicals, like the one that took place in the chemical foam extinguishers used in the 1800s. Today, this type of foam is rarely used because it requires the combination of two different chemicals before the foam can be made, which may be difficult to carry out at a fire scene. Also, because of the large amount of powders required, this type of foam has become obsolete in today's fire service. Mechanical foams are produced when water and foam concentrate are mixed in the appropriate amounts or proportioned, and the ratio of foam concentrate to water must be correct to ensure that the foam creation and operation is effective. The class of materials involved in the spill or fire, which dictates the type of fire, determines the percentage of foam needed. Hydrocarbon fuels such as gasoline, jet fuel, and kerosene have a lower surface tension than water. When these types of fuels and water are mixed, the two fluids quickly separate and the fuel rises to the top and the water remains on the bottom. When foam concentrate or foam liquid is mixed with water, the surface tension is reduced. This allows the foam solution to float on the surface of the fuel. Its presence will suppress the vapors both by separating the fuel from oxygen and the ignition source and by cooling the fuel below its ignition temperature. Producing finished foam has become a very common task for operators of fire apparatus. The modern foam systems today are very user-friendly, and the easy setup and application steps have made foam an important tool for firefighters to have at their disposal. Now let's talk about foam characteristics. Good foam must have the right combination of physical characteristics if it is to be effective. Specifically, it must have a good knockdown speed and flow as well as good fuel resistance. Knockdown speed and flow comprises the time required for a foam blanket to spread out across a fuel surface. The foam must also be able to flow around obstacles to achieve complete extinguishment and vapor suppression. Foam must have good heat resistance so that it can avoid breakdown from the effects of direct flame contact with burning fuel vapors or the heat generated from metal objects. Fuel resistance is foam's ability to minimize fuel pickup, which is the absorption of the burning fuel into the foam itself. This oleophobic, which is ability to shred hydrocarbons, quality reduces the amount of fuel saturation in the foam and prevents the foam blanket from burning. Ideally, foam will produce a good vapor suppressing blanket. A vapor-tight foam blanket reduces the generation of flammable vapors above the fuel surface and minimizes the chance of reignition. And this is illustrated in figure 14-5 in your text. When used on polar solvent fuels, foam must also be alcohol resistant. Given that alcohol readily mixes with water and that foam is mostly water, a foam blanket that is not alcohol resistant will quickly dissolve into the fuel and be destroyed. Now let's talk about some different foam classifications, and we'll start with Class A foams. Class A foams are used on ordinary combustible materials such as wood, textiles, and paper. It's also effective on organic materials such as straw and hay, and sometimes they're referred to as wetting agents. They're very effective because they improve the penetrating effect of water and allow for greater heat absorption. According to foam manufacturers, these wetting agents can extinguish fires involving Class A materials as much as 20 times faster than water itself, and this is shown in figure 14-6 in your text. Particularly useful for protecting buildings in rural areas during forest and brush fires when the water supply is limited is what a water penetrating foam is good for, and it can also be used as a fire barrier, that is, an obstruction to the spread of fire. A thick blanket of Class A foam applied to an exposure can provide adequate protection for that exposure, thereby preventing the spread of the fire, and this is shown in figure 14-7 in your text. Class A foams are also used by many fire departments while performing initial attack and overhaul of fires. This increases the effectiveness of the water as an extinguishing agent by reducing the surface tension of the water. As a result, the water penetrates dense materials instead of running off of the surface. In addition, more heat is absorbed by the water. The foam also keeps water in contact with unburned fuel to prevent its ignition, and it can be added to water streams and applied with various types of nozzles. Class B foams are used on hydrocarbon, combustible fuels, or polar solvent fires. Please see Table 14-1 on page 330 of your text for a little more information on this. Polar solvent and water miscible fuels such as acetone mix readily with water and will degrade the effectiveness of ordinary Class B foam. So Class B foams are divided into the following categories: protein foams, fluoroprotein foams, and alcohol-resistant film-forming fluoroprotein foams. That's known as AR-FFP. Now, wetting agents and foams in Class B foams is what we're going to talk about now, and there has been a significant amount of discussion over the years regarding nearly every wetting agent, additive, water additive, and foam. Most of these discussions have been and continue to be clouded with misinformation and misunderstanding about each extinguishment medium. It is common for firefighters to make the mistake that a wetting agent is a foam because they're very similar by sight, and the containers may be the same and they may have a similar appearance upon application. However, they are very different in chemical makeup. A wetting agent reduces the surface tension of the water and enhances penetration into the fuel that is burning. A foam creates a stable mass of small air-filled bubbles with a lower density than oil, gas, or water and will float on top of burning fuel, creating a blanket that separates the fuel from the air, lowering the temperature and suppressing the vapors. When choosing a wetting agent or a foam, make sure the foam or wetting agent is listed by a national recognized listing agency. Always make sure you follow the manufacturer's guidelines in the foam or wetting agent, and always use caution when using foam or wetting agents or the following types of fires. Those are flammable and combustible liquids and cooking media such as vegetable oil or animal fats. Over the past 35 years, there have been some significant scientific advancements for both wetting agents and foams. It is wise to always ensure that the product is listed by an independent testing firm and meets the current National Fire Protection Association, or NFPA, standards. It is just as important to read and understand the manufacturer's specifications and have clear understanding of the limitations of both wetting agents and foams. The future may bring such wetting agents that can handle both Class A and Class B fires with the recent development of NFPA 18A, which is the standard on water additives for fire control and vapor mitigation, and testing criteria designed to test water additives to suppress both classifications of fires with one extinguishing agent. But as of right now, there is no single agent. Now let's discuss protein foams. Protein foams are used to extinguish Class B fires involving hydrocarbons. These agents can protect flammable and combustible liquids where they are stored, transported, and processed. Protein foams contain naturally occurring proteins, that is, animal byproducts, as the foaming agent. They are based on keratin protein derived from sources such as chicken feathers or animal hooves that has gone through the process of hydrolysis. Protein foams also include stabilizers and inhibitors which prevent corrosion and control viscosity. They produce highly stabilized mechanical foam with good expansion properties, excellent heat and bump back resistance, and good drainage characteristics. Regular protein foams may be created using either fresh or salt water, and these foams must be properly aspirated. They should not be used with non-aspirating structural fog nozzles. Regular protein foams have slower knockdown characteristics than other concentrates, but they provide long-lasting foam blanket after the fire is extinguished. This is shown in Figure 14-8 in your text. Now, fluoroprotein foams or also known as FP, consist of hydrolyzed protein, stabilizers, preservatives, and synthetic fluorocarbon surfactants. They're used for hydrocarbon vapor suppression and extinguishment of fuel in-depth fires. FP, or fluoroprotein foams, are effective for subsurface application to hydrocarbon fuel storage tanks. Fluoroprotein foams are intended for use on hydrocarbon fuels and some other oxygenated fuel additives. They have excellent heat and burnback resistance. They maintain good foam blanket after the extinguishment of the fire, and the addition of surfactants makes the foam much more fluid. This increases the knockdown rate and provides better fuel tolerance than is possible with protein foam. Fluoroprotein foams may be created using either fresh or salt water. Because they must be properly aspirated, these foams should not be used with non-aspirating structural fog nozzles, and this is shown in figure 14-9 in your text, and you can see an example of that nozzle here on this slide. Film foaming fluoroprotein foam, or triple FP, includes protein and fluorochemical surfactants. With these foams, the fluorochemical surfactants are generally presented in higher concentrations than in standard FP. Triple FP is able to form a vapor sealing film on nonpolar solvents. The knockdown performance is improved because the foam releases an aqueous film on the surface of the hydrocarbon fuel. Now, alcohol-resistant film-forming fluoroprotein foams can be used on both hydrocarbon and water-soluble fuels. On hydrocarbon fires, the film-forming ability of this foam allows for rapid fire knockdown and excellent burn-back resistance. On water-soluble fuels, its resistance to water-soluble solvents arises because a cohesive polymeric membrane forms on the fuel surface. This protects the foam from contact with polar fuels. AR triple FP is basically triple FP with polysaccharide polymer additive. Where polar solvents will destroy triple FP, the polymer in AR triple FP forms a membrane to separate the polar solvent from the foam blanket. Now let's discuss synthetic foams. Aqueous film-forming foam, or AFFF, is based on combinations of fluorochemical surfactants, hydrocarbon surfactants, and solvents. AFFF requires a low-energy source to produce high-quality foam. This foam can be applied using a variety of foam application systems. Because of the versatility of AFFF, it is used by the majority of municipal and airport fire departments in North America. AFFF is also used at refineries, manufacturing plants, and other operations involving flammable liquids. AFFF is very fluid and quickly flows around obstacles and across a fuel surface. Its ability to flow quickly allows AFFF to achieve a very fast knockdown of hydrocarbon fires. This foam can be used as a premixed solution, is compatible with dry chemical agents, and can be created using either fresh or salt water. AFFF consists of a mixture of synthetic foaming agents and fluorochemical surfactants. It extinguishes fire by forming an aqueous film on the fuel surface, and this film comprises a thin layer of foam solution which quickly spreads across the surface of a hydrocarbon fuel, creating an extremely fast fire knockdown. This is shown in figure 14-10 in your book. The surfactants found in AFFF reduce the surface tension of the foam solution, which allows it to remain on the surface of the hydrocarbon fuel. The aqueous film is formed by the action of the foam solution draining from the foam blanket. Aspirating foam nozzles should be used to apply AFFF to ensure maximum performance. Nozzles that will be used for foam application must be tested for compatibility with the foam system being used. Let's discuss alcohol-resistant aqueous film-forming foams. This comprises a combination of synthetic detergents, fluorochemicals, and high molecular weight polymers. Neither polar solvents nor water-miscible fuels are compatible with non-alcohol resistant foams. Common polar solvents include solutions of the following compounds: alcohols, including isopropyl, methanol, and ethanol; esters, including butyl and acetate; ketones, including methyl and ethyl ketone; and aldehydes, including acetaldehyde and tolualdehyde. When non-alcohol resistant foam is applied to the surface of a polar solvent, the foam blanket quickly spreads down into a liquid and mixes with the fuel. By comparison, AR-AFFF acts like conventional AFFF on hydrocarbon fuels, forming an aqueous film on the fuel surface. When applied to polar solvents, however, AR-AFFF forms a polymeric membrane on the fuel surface. This membrane separates the fuel from the foam and prevents destruction of the foam blanket. AR-AFFF is one of the most versatile types of foam. It provides good knockdown and burn back resistance and has a high fuel tolerance on polar solvent and hydrocarbon fires. Synthetic detergent foams or high expansion foams are highly effective in confined space firefighting operations and in areas where access is limited or entry is dangerous to firefighters. Some examples include basements, shipboard compartments, warehouses, aircraft hangars, and mine shafts. These types of foams can be used in both fixed generating systems and portable foam generators. High expansion foams can be used on either Class A or Class B fires. Each foam manufacturer offers a different product. It is your responsibility as a driver-operator to determine which foam can be used on the fire you're facing. High expansion foams are based on combinations of hydrocarbon surfactants and solvents, and they are useful on fuels such as liquefied natural gas for vapor dispersion and control. In certain concentrations, these foams are effective extinguishing agents for flammable liquid spill fires of most types. The foam concentrates are normally proportioned in ratios between 1 to 3% for these uses. Please see figure 14-12 in your text for an example. Fire control and extinguishment are achieved by rapid smothering and cooling of the fire. High expansion foams have a tremendous smothering and steam generation effect because the water contained in them is divided into such fine particles, which enhances the heat absorption quality of the water. This factor also presents a potential hazard, however. Care must be taken with regard to electrical power sources in the area when this type of foam is applied. Remember that foam is mostly water and presents the same electrical shock potential to firefighters as does water application by itself. Now let's talk about foam concentrates. Foam concentrates are designed to be mixed with water at specific ratios. And here is table 14-2, which is also in your text. Please make sure that you review it. Foam concentrate ratios vary from 0.1 to 1% for Class A foams and from 1 to 6% for Class B, i.e. 1 to 6% foam concentrate to water ratio in the final foam product. The amount of concentrate varies depending on the manufacturer, the type of application, and the type of fuel. For example, when using Class A foam for initial fire attack on a vehicle fire, you might use a 0.3 or a 0.5% ratio of foam concentrate to water. This ratio allows the foam to help extinguish the fire without creating too much foam. If you were supplying a hose line that was spraying foam on a house to protect it during a brush fire, you might increase the ratio to 3%, thereby creating a thicker foam that would last longer and protect the house for an extended period, depending on your department's standard operating procedures / standard operating guidelines and the manufacturer's recommendations. The foam concentrate must be proportioned at the percentage listed by its manufacturer. Each foam is tested and approved for certain types of fires and at specific ratios. Always follow the manufacturer's guidelines when using this product. The foam concentrates are manufactured at different percentages for a variety of reasons. Thus, the product's components include the concentrate, which is a unique chemical compound, plus any freeze protection additives. Military use specifications and cost are some of the basic factors that determine the percentage of concentrate used in any particular situation. The current trend is to keep foam concentrate percentages as low as possible for several reasons. Lower proportioning means less bulk in storage for fire departments. They also mean that you can double your firefighting capacity by carrying the same volume of foam concentrate, and you can cut your foam supply in half without reducing the company's fire suppression capabilities. Lower proportioning rates can reduce the cost of fixed foam system components and concentrate transportation costs. Historically, foam concentrates were manufactured for use at ratios between 3 and 6%. Today, foam concentrates are produced for ratios as low as 0.1% and as high as 6%. This depends on the liquid fuel and the manner in which the foam is to be used. Remember, the foam concentrate percentage must match the fuel to which the foam is being applied. If a mismatch occurs, the foam may not be effective in controlling the fire. Alcohol-resistant foams can be used effectively on both hydrocarbon and polar solvent fuels. ARAFFF is a commonly used concentrate for this purpose. It is available in a variety of percentages. For example, ARAFFF concentrate is available as a 3%/3% product, meaning that it can be used at 3% for incidents involving either hydrocarbon fuels or polar solvents. It is also available as a 3%/6% mixture. This means that foams for hydrocarbon-based incidents are proportioned at a 3% concentration ratio, and foams for incidents involving polar solvents are proportioned at a 6% concentrate ratio. Another option is available is ARAFFF 1% 3% product. This means foams for hydrocarbon-based incidents are proportioned at 1%, and foams for polar solvent-based incidents are proportioned at 3% or lower for newer concentrates. Given the many types of foam concentrates available, the selection of the right concentrate is critical to the safe and effective handling at an incident. Knowledge of the foam types and systems available will assist incident commanders, ICs, and their ability to mitigate an incident. The importance of pre-planning and training for these types of incidents cannot be stressed strongly enough. Now let's discuss foam expansion rates. The foam expansion rate is the ratio of finished foam to foam solution after the concentrate is mixed with water, agitated, and aspirated through a foam making appliance. For example, a low expansion foam has an expansion ratio of 20:1. This means that 20 parts of finished foam are produced for every 1 part of foam solution. The air inside the bubbles makes up the expanded part of the finished foam. NFPA 11, which is the standard for low, medium, and high expansion foam, classifies foam concentrates into 3 expansive ranges: low expansion, medium expansion, and high expansion. Low expansion foam has a foam expansion ratio of up to 20:1. This type of foam is primarily designed for use on flammable and combustible liquids. Low expansion foam is effective in controlling and extinguishing most Class B fires, and special low expansion foams are also used on Class A fires where penetrating and cooling effect of the foam solution is important. Medium expansion foam has a foam expansion rate in the range of 20:1 up to 200:1. This kind of foam is used primarily to suppress vapors from hazardous chemicals. Foams with expansion ratios between 30:1 and 55:1 have been found to produce the optimal foam blanket for vapor mitigation of highly reactive chemicals and low boiling point organics. High expansion foam has a foam expansion rate in the range of 200:1 up to 1,000:1. This type of foam is designed for confined space firefighting, and this foam concentrate consists of synthetic detergent type foam used in confined spaces such as basements, mines, shipboard, and aircraft hangars. Now let's discuss proportioning of foam concentrate. The application of foams at the proper percentage depends on the foam concentrate being mixed at the proper percentage with water. The percentage of concentrate may be introduced into the water stream by any of several methods. It is imperative that you become familiar with the type of equipment that is used in your agency's foam operations. As the driver-operator, you have the responsibility to produce effective foam streams. You must have the knowledge of all aspects of foam operations so that the foam produced will do what it is intended to do. Foam that is not mixed at the proper percentage or is used on a material or product for which it was not intended will not only be ineffective, but can also put firefighters on hose lines in danger. To produce finished foam, the water, air, and foam concentrate must be mixed at the proper ratio. Foam concentrate must be added to the water that is flowing from a discharge line to form the proper mixture. This mixture or percentage is based on the type of foam concentrate used, the type of material involved in the incident, and the type of equipment used to produce the finished foam. The foam proportioner is the device that mixes the foam concentrate into the fire stream in the proper percentage. The two types of proportioners, adductors and injectors, are available in a wide range of sizes and capabilities. Foam solution can also be produced by batch mixing or pre-mixing. Batch mixing is the process of pouring foam concentrate directly into the fire apparatus water tank, thereby mixing a large amount of foam at one time. This is illustrated in Figure 14-13. While this method requires no special appliances, some problems may arise with batch mixing. The foam solution is corrosive to the apparatus's pipes, pump, and water tank, and it is difficult to adjust and maintain the correct application rate, especially if additional water is supplied for an external source. The addition of foam solution may also cause the gauges to become inaccurate, such that the water tank overflows with foam when the pump is recirculating the mixture. Class A foam concentrates that are batch mixed must be used within 24 hours if they are to be effective. As with some of the other systems used to create foam, all discharges will deliver foam when it is supplied from an onboard tank. When the water tank is empty, however, there is no longer any foam available, so a new batch has to be mixed. As long as you know the amount of water in the onboard water tank, then you can simply add the foam concentrate to achieve the desired foam solution percentage. For example, if the water tank on the apparatus holds 500 gallons of water and you want to use Class A foam at 1%, you would add 5 gallons of foam concentrate with an inline foam adductor. To prepare foam through batch mixing, follow the steps in Skill Drill 14-1. Pre-mixing of foam solutions is a technique that usually is reserved for portable fire extinguishers. Many fire departments use these extinguishers filled with pre-mixed foam solutions for small flammable liquid spills at the scene of a motor vehicle accident. They are quick and easy to deploy, but contain a limited amount of foam and should be applied only to small fires or fuel spills. Always refer to the foam manufacturer's recommendations regarding how long the foam concentrate should be used after mixing it with water. Foam adductors is what we're going to discuss now. An induction involves the use of an inductor to introduce the appropriate amount of foam concentrate into a stream of water flowing from a discharge. An inductor is an appliance that uses the Venturi principle, or i.e. suction effect, to introduce foam concentrate into the water stream. An inductor can be built into the plumbing of an engine, or a portable inductor can be inserted into an attack hose line. A foam inductor is usually designed to work at a predetermined pressure and flow rate, and its metering valve can be adjusted to set the percentage of foam concentrate that is inducted into the stream. For example, a simple inline inductor has a small pickup tube that is submerged in foam concentrate. As the water travels through the inline inductor, it draws foam into the water at the desired percentage using the Venturi principle. Two types of inductors are used in the fire service today: inline inductors and bypass inductors. Inline inductors have long been used to proportion foam, and that's illustrated in Figure 14-14. These appliances may be mounted permanently on the apparatus. Alternately, they may be portable and connected anywhere along the hose lay. Inline inductors should be used only for the application of foam. Those mounted permanently to the fire pump are dedicated to one foam discharge. Such pump-mounted inductors are inline devices dedicated to producing foam only. By comparison, bypass inductors are permanently mounted appliances that can be used for water or foam application depending on what is required at the incident scene. As mentioned earlier, inductors use the Venturi principle to mix a specific amount of foam concentrate into the water stream. Specifically, a suction effect is created at the narrow inlet to the inductor. This narrow passage increases water velocity, which reduces the water's pressure as it flows into the larger induction area. Foam concentrate is introduced into the inductor using a metering valve. This allows the driver-operator to adjust the percentage of foam concentrate being added to the water stream. Most inductors are calibrated to flow the rated capacity at 200 pounds per square inch inlet pressure. An inductor inlet pressure of 200 psi is necessary to overcome friction loss through the inductor as well as the friction loss between the inductor and the nozzle. Inductors are available for delivering flow rates of 30, 60, 95, 125, and 250 gallons per minute. The nozzle used with the system must match the flow rating of the inductor. It is critical that the inductor and nozzle gallon settings match because the inductors need certain velocities of water flowing through them to allow proper mixing of the foam concentrate. Mismatched equipment can result in either too rich or too lean a foam in the fire stream. Always allow the manufacturer's recommendations or follow them when selecting nozzles to use with foam inductors. The metering device controls the flow of concentrate into the inductor, and the example is shown in Figure 14-15. The amount of foam concentrate introduced into the water stream is controlled by adjusting the metering valve. As the driver operator, you should adjust the metering valve to the desired percentage to handle the situation at hand. Metering valves have adjustable settings that range from 0, which is the closed position, up to 6%. The percentage set on the metering valve will be achieved only if the inlet pressure at the inductor matches the manufacturer's recommended inlet pressure. If the inductor is operated at less than the recommended inlet pressure, a lower flow of water will go through the inductor. This lower flow of water will in turn result in a higher percentage of foam concentrate being introduced into the water stream. Depending on the available supply of foam concentrate, unnecessary wastage of foam concentrate will occur and the driver operator could run out of foam before the fire is extinguished. The opposite will occur if the inlet pressure into the inductor exceeds the pressure recommended by the manufacturer. A higher inlet pressure at the adductor will cause the foam solution to have a lower percentage of concentrate. This could affect the company's ability to handle the situation in which the foam is being applied. Operating the inline adductor. The inline adductor is a very simple, efficient, and inexpensive type of foam proportioner. Many fire departments still use it as standard equipment to create foam at their fire scenes. These devices are constructed out of rugged brass alloys and, if properly maintained, can last for many years. An inline adductor is attached to the hose line no more than 150 feet from the nozzle and no more than 6 feet above the surface of the foam concentrate. It's this placement that makes it easy to set up and take down. Although this type of device is simple to operate, some very specific instructions must be followed to ensure its proper use. To operate an inline adductor, follow the steps used in Skill Drill 14-2. Let's talk about the around the pump proportioning system. It operates on the same principle as the inline or bypass adductor system. It diverts a portion of the water pump's output from the discharge side of the pump and sends it through an adductor. A vacuum is created at the adductor's foam concentrate inlet, which draws foam concentrate through the metering valve and into the adductor. The foam solution of water and concentrate is then sent to the suction side of the water pump, where it mixes with the incoming water and is distributed throughout the discharge piping. The AP system offers several advantages over other foam creation methods. The process used for engaging the pump is the same for water or foam operations. The variable flow discharge rate allows for adjustment of the foam depending on the specific application. Variable pressure operations are possible, usually within a range of 125 to 250 psi. There are no back pressure restrictions because the system is not affected by hose length or elevation loss. And there are no nozzle restrictions because the system will operate with any size or type of fixed gallon nozzle. AP systems also have certain limitations with which you must be familiar. All discharges will have either foam or water available at the same time. You will not be able to supply some lines with water and other lines with foam simultaneously. Either one or the other must be chosen. The maximum inlet pressure to the water pump cannot be more than 10 psi. Any pressure greater than 10 psi will affect the operation of the adductor. Some manufacturer systems are designed to operate with an inlet pressure as much as 40 psi. Check your system's operating instructions for the proper inlet pressure. AP systems are intended to operate with water supplied from the onboard tank or from a draft. As a consequence, use of a pressurized source, like a hydrant or relay, will affect the operation of the system. Most fire apparatus with AP systems have a direct tank fill that does not go through the fire pump. In such systems, the tank is filled directly from the pressurized source and the water pump supply comes from an onboard tank. All discharges must be flushed after the foam operation is ended, even if they were not used. When using automatic nozzles, the flow must be determined to ensure that you set the metering valve correctly. The appropriate setting for the metering valve depends on the type of concentrate being used, the percentage needed for the incident, and the rate of flow in gallons per minute. When the flow rate changes, such as when a line is shut down, the metering valve needs to be adjusted to accommodate the new flow. To operate an AP system, follow the steps in Skill Drill 14-3. Now let's talk about a balanced pressure proportioning system. Balanced pressure systems are extremely versatile and accurate means to deliver foam. The system uses a diaphragm-type pressure control valve to sense and balance the pressures in the foam concentrate and water lines to the proportioner. The valve keeps the foam concentrate and the water pressure in balance by allowing excess foam concentrates to return return to the foam concentrate storage tank, and this is shown in figure 14-16. This proportioning occurs automatically for flows within the operating limits of the foam concentrate pump and the discharges. The foam concentrate pump is a separate pump that supplies foam concentrate to the pressure control valve and the radio controller. The pressure control valve act is a balancing valve. It maintains equal foam concentrate and water pressures at the radio controllers. Thus, the pressure control valve automatically maintains equal pressure within the foam creation system. Unused foam concentrate from the foam pump discharge is returned to the foam concentrate storage tank. A radio controller is a device required for each foam outlet to proportion the correct amount of foam concentrate into the water stream over a wide range of flows with minimal pressure loss. This modified Venturi device provides a metered pressure drop for controlled injection of foam concentrate into a reduced pressure zone. Metering valves receive foam concentrate from the foam pumping out, or from the foam pump, and in turn discharge that concentrate to the individual radio controllers. These devices function as a concentrate shutoff. They also allow you to adjust the foam concentrate for each discharge. The metering valve setting is available and usually ranges from off to 6%. The foam solution can be produced at any radio controller / discharge connection by opening the corresponding foam solution metering valve to the desired percentage rate. Plain water is simultaneously available at the remaining discharge connections. A duplex gauge at the pump panel allows the driver operator to monitor the foam concentrate and water pressures, and this is shown in figure 14-17, which you also see here on the slide. These pressures should be balanced or equal, a feat that is achieved automatically by the balanced pressure system. For example, if the flow of water in the pump increases, the system will rebalance itself to compensate for the additional pressure to maintain an accurate flow of correctly proportioned foam solution. A manual throttling control valve located at the pump panel enables the driver operator to override the automatic system by increasing or decreasing foam concentrate pressure in case a problem occurs within the system. Many balanced pressure systems are equipped with a foam heat exchanger. The heat exchanger uses water as its cooling source and prevents the foam concentrate from overheating. To operate a balanced pressure proportioning system, follow the steps outlined in Skill Drill 14-4. Injection systems use an electrically operated variable speed foam concentrate pump that directly injects foam concentrate into the discharge side of the pump manifold. Injection systems are the most common type of system in use today. They are designed with Class A foam concentrates and with many Class B foam concentrates depending on the viscosity of the concentrate. Injection systems depend on the water flow for their operation. They will adjust the amount of foam concentrate being injected into the discharge manifold depending on the flow rate of gallons per minute and the percentage set by the driver operator. The foam concentrate pump will also adjust its operating speed depending on the amount of water flowing, and injector systems are not affected by changes in suction and discharge pressure. The only limitation on such a system is the rated capacity of the foam concentrate pump. There are many different sizes of foam concentrate pumps that are available, so it is imperative that you know the limits of the specific pumps used on your department's apparatus. Direct injection systems are very user-friendly. A control unit located at the pump panel allows the driver operator to operate the foam system. This control unit has an on-off button that starts and secures the foam operations. It also allows the driver operator to monitor the water flow rate, concentrate injection percentage, total amount of water flowing, and the total amount of concentrate used. With injection systems, the driver operator can adjust the foam concentrate percentage while the system is in operation. Concentrate injection rates can be set anywhere in the range of 0.1 to up to 10%. These percentages, which can be changed in 0.1% increments, are selected using a button on the control unit. Injection foam systems can be used with standard nozzles, aspirating nozzles, and compressed air foam systems. These systems can be set up to supply multiple discharges on the water pump. Depending on the apparatus, the foam concentrate is injected into the discharge manifold at only one injection point. Therefore, all discharges that are piped from the foam discharge manifold will be capable of delivering foam. Although other discharges are not piped to the foam manifold and are capable of discharging water, all discharges from the foam manifold will produce foam. To operate an injector foam system, follow the steps outlined in Skill Drill 14-6. Compressed air foam systems combine compressed air and foam solution to create a finished foam. They are designed for quick and effective fire attack and exposure protection. This type of system is generally used to generate Class A foam, specifically a high-quality finished foam that clings to vertical surfaces, and this is shown in Figure 14-18. This foam holds moisture on the fuel surface, where it evaporates or penetrates, thereby cooling and lowering the fuel's temperature. The production of finished foam depends on the correct mixture of water, foam concentrate, and air within the CAFS. This kind of system uses a fire pump, a foam concentrate injection system, and an air compressor to produce high-quality finished foam streams inside the fire apparatus piping. The foam aeration on the CAFS takes place at the pump discharge, that is, air introduced at the pump. Thus, the foam solution is mixed with air prior to reaching the end of the hose line. This type of foam or system allows for more uniform bubble structure and a better finished foam. A CAFS has some key benefits for firefighting operation. The quality of the foam is greatly improved due to its consistently smaller bubble structure. The foam produced by the CAFS works 4 to 5 times faster than water in suppressing fire. A CAFS uses less water, thereby reducing the extent of water damage. The quick knockdown, fast fire suppression, and less extensive water damage associated with this type of foam system may help fire investigators in determining the cause of the fire. The reach of the fire stream is improved, and the foam discharge will be lighter than water because the discharging foam is a mixture of foam solution and air. The improved stream reach allows for making the initial fire attack from a greater distance, and this reduces risk of injury to firefighters. The weight of the attack line is less than half of a line containing just water. CAFS hose lines are typically filled with approximately 30% compressed air. Firefighters will be able to move the lines more easily, which will reduce their fatigue. Because the hose is filled with air, friction loss is insignificant, and there is not the normal pressure loss with elevation. Driver operators should also be aware of some potentially problematic issues dealing with the CAFS. The driver operator needs to be familiar with the operation of the air compressor. Water and air are incompressible, so foam solution must be present in the water stream prior to injection of compressed air. If the foam concentrate is not present, unmixed water and air will be discharged in an erratic manner called slug flow, and the hose line could be jerked out of the hands of the firefighters. A CAFS burst hose line will react more radically due to the air in the line. Nozzle reaction is greater due to air in the CAFS hose, so nozzles should be opened more slowly. Operating a CAFS is dependent on your apparatus-specific system. Always refer to the manufacturer's recommendations and procedures for your system's make and model. In general, to operate a CAFS, follow the steps in Skill Drill 14-6. Now let's discuss nozzles. Nozzles are an important part of all foam operations. The proper nozzle is needed for firefighters to be able to produce a good quality foam blanket. The following types of nozzles are available: medium and high expansion foam generators, master stream foam nozzles, air aspirating foam nozzles, smoothbore nozzles, and fog nozzles. Medium and high expansion foam generators are what we're going to talk about first, and foam generators produce medium and high expansion foams, and these devices are usually consist of either a mechanical blower or water aspirating appliance. A water powered aspirating type of generator uses a water motor driven fan to produce the required airflow. Some water powered high expansion generators are designed to achieve expansion rates of as much as 1,000 gallons of finished foam for every 1 gallon of foam solution. The final expansion ratio achieved depends on the generator used, the solution flow rate, and the operating pressure. Mechanical generators operate similarly to water aspirating generators, and this is shown in illustration 14-19. The difference is that the mechanical generator is electrically powered by a fan which forces the airflow through the unit. High expansion foam systems are designed for use in total flooding applications and are effective at the following locations: mines, warehouses, aircraft hangars, basements, storage buildings, paper warehouses, machinery spaces, hazardous waste facilities, and wildland fire breaks. High expansion foams produce large volumes of foam that exclude oxygen from the incident area. In addition, the low water content of this type of foam reduces water damage. Master stream foam nozzles allow operators to deal with large incidents where handline nozzles are not able to handle the demands for foam suppression. They can be supplied from the fire apparatus's onboard systems. Alternately, they can have an adductor as part of the nozzle. A pickup tube draws the foam into the master stream nozzle, and this tube is placed into the foam concentrate supply and operated as an adductor system. Master stream foam nozzles can be mounted permanently on the fire apparatus, can be removable so that they can be used as a portable unit, or can be strictly portable devices. Air aspirating foam nozzles are designed to mix air with the foam solution as it is discharged. This effect is achieved without having to add a clamp-on tube to a fog nozzle. These foam nozzles are designed to aspirate the foam solution to produce good quality finished foam. Smoothbore nozzles are the nozzle of choice when using a CAFS. Because the aeration of the foam solution takes place in the piping and hose, the finished foam will be discharged at the nozzle. Application, not aeration, is the major concern when smoothbore nozzles are used with a CAFS. Fog nozzles can be used to produce finished foam. When the incident involves polar solvent fuels, for example, fog nozzles may not deliver a foam quality that is able to extinguish the fire. Foam aeration tubes are available that can easily and quickly be clamped onto the end of a fog nozzle to aerate the foam solution more efficiently. Now let's discuss foam supplies. Foam concentrate is stored in containers that can range in size from 5-gallon pails up to 55-gallon drums, and that's shown in illustration figure 14-20. Totes and trailers of foam concentrate are available in different sizes as well, ranging from 100 to 1,000 gallons of foam concentrate. Foam may be stored in its container without any change in its original physical or chemical characteristics. Freezing and thawing usually will not have any effect on modern foam concentrates. It is important to check with the concentrate manufacturer for technical information on the concentrate's properties, however. The shelf life of foam concentrate will vary depending on the type of concentrate. Typically, protein concentrate has a shelf life ranging from 7 to 10 years. Synthetic concentrates and high expansion concentrates have a shelf life of 20 to 25 years. The environmental impact of foam has been a concern for many years. Many types of foam have undergone testing to assess their effects on the environment. Information regarding the toxicity of foam concentrates is usually available from the product environmental data sheets, material safety data sheets, product technical bulletins, and toxicity summary sheets. The manufacturer or supplier of the foam concentrate is a primary source for researching this information. Now let's talk about applying foam. With Class A foam, it's used for structural firefighting and is becoming more common in practice. The benefits of using foam to extinguish a Class A fire or an incident involving three-dimensional fuels have been proven through testing done by manufacturers and fire departments. The use of Class A foam for firefighting is similar to the use of water. Although the application methods are the same, the results will probably be better with the foam. Training and experimentation with Class A foam in actual fire situations is not recommended due to safety concerns. Instead, the confidence and experience needed in operating foam systems can best be achieved with live fire training. To apply a Class A foam on a fire, follow the steps in Skill Drill 14-7. Class B foam. The methods used for Class B foam or Class B fires differ from those used when applying Class A foam on a Class A fire. Directing a Class B foam stream onto a Class B fire can disrupt the fuel and cause the fire to spread. Plunging the stream into an existing foam blanket will allow vapors to escape. This can result in a spreading, reignition, or flare-up of the fire. To avoid these problems, three methods are used to produce foam blankets on Class B fires: the roll-on method, breakdown method, or rain-down method. The sweep or roll-on method should be used only on a pool of flammable product that is located on open ground. With this technique, foam is placed on a fuel surface by directing the foam stream onto the ground in front of the product involved. The foam will then roll onto the surface of the material involved. It may be necessary to move the hose line to a different position to achieve total coverage. You may also need to use multiple lines to cover the material. If the crew uses multiple hose lines, they need to maintain awareness of the positions of other firefighters operating in the area. A coordinated attack should be conducted by the IC. A safety officer should be on the scene. To perform the roll-on method, follow the steps in Skill Drill 14-8. The bank shot or bank down method is a method that's employed at fires where the firefighter can use an object to deflect the foam stream and let it flow down the burning surface. This application of foam should be as gentle as possible to avoid agitating the material involved. If the material is located in an area where there is a well, a tank, or another vertical object, then the foam can be directed at and allowed to run down that object. This approach will allow the foam to spread over the material and form a foam blanket. To perform the bank down method of applying foam, follow the steps in Skill Drill 14-9. The rain down method can be used where there is no vertical object to use for a bank shot and it would be too dangerous to get close and use the roll-on method of foam application. This foam application technique consists of lofting the foam stream into the air above the material and letting it fall gently onto the surface. It can be an effective method as long as the foam stream can be completely covering the material involved. Two caveats apply. First, this method might not be effective when wind conditions are unfavorable, and second, the covering of the foam needs to be monitored. The fire itself may vaporize the foam stream, producing reduced results. To perform the rain down method, follow the steps in Skill Drill 14-10. Now, with foam compatibility, Class A concentrates and Class B concentrates are not compatible. Mixing these different classes of concentrates may cause the concentrate to gel and hinder the operation of foam proportioning equipment. Class B foam concentrates may not be compatible with each other. Check with the foam manufacturer for information or compatibility of a particular type of foam. Make sure onboard tanks of on fire apparatuses are properly marked. Many fire apparatuses carry onboard water, Class A foam concentrate, and Class B foam concentrate tanks. In some instances, foam concentrate has been poured into the wrong tank with undesirable results. So in summary, while water is effective in suppressing fires, foams have added a new dimension to firefighting strategies. Foam for firefighting consists of a stable mass of small air-filled bubbles. It has a lower density than oil, gasoline, or water and will float on top of the fuel. The way that foam works to help extinguish a fire is very simple. Once applied to the burning fuel, the foam will float on top of it, forming a blanket on the surface. This blanket, if applied correctly, will stop or prevent the burning process by separating the fuel from the air, lowering the temperature of the fuel, and/or suppressing the release of flammable vapors. Foam is made up of 4 components: water, foam concentrate, mechanical agitation, and air. Firefighting foams are classified as either Class A or Class B. Foam concentrates are designed to be mixed with water at specific ratios ranging from 1% to 6%. The foam expansion rate quantifies the ratio of this finished foam to foam solution after the mixture is agitated and aspirated through a foam making appliance. Foam cannot be produced if it is not proportioned properly. Several types of foam application systems are available, ranging from basic operations to more advanced systems. With the proper training, these systems can be very user-friendly and will produce a good quality finished foam. The proper nozzle is needed for firefighters to be able to produce a good quality foam blanket. Foam concentrate is stored in containers of various sizes, including 5-gallon pails, 55-gallon drums, totes, and trailers. Knowing the several accepted methods for applying foam is important for driver operators because they may have to use a hand line to apply foam or may need to assist other firefighters in the application method. Class A concentrates and Class B concentrates are not compatible, and mixing these different classes of concentrates may cause the concentrate to gel and hinder the operation of foam proportioning equipment. Thank you for your time and attention, class. I appreciate it. Please make sure you review everything carefully. Let Chief Brakebill know if you have any questions, either by contacting him on phone or through email. And again, thank you for your time and attention. We'll see you next class.